There are two basic types of telescope, refractors and reflectors. The one I'm looking at now is a refracting telescope which uses a convex or converging lens to capture and focus light. Whereas on the right, we have a reflecting telescope using a parabolic, concave or converging mirror to capture and focus light. The objective element collects as much light as possible and focuses the light to a small, bright image. This image is then magnified with an eyepiece lens so that astronomical objects such as double stars, lunar maria, globular clusters, nebulae and galaxies can be observed in much more detail, that is higher resolution, and are much brighter than when looking at them with just the naked eye. A telescope's size, or aperture, is the diameter of its objective lens or mirror, usually quoted in centimetres or metres. This should be of prime importance when using or purchasing a telescope, because the larger the size, the more light enters the telescope, making images not only brighter, but the sharper the image, that is, the higher the amount of detail that can be resolved. The resolution also depends on the wavelength of light entering the telescope. The longer the wavelength, the poorer the resolution. So in theory, the amount of detail visible in images of pink or red nebulae is not as good as that is seen in blue nebulae surrounding young stars. And I've put some images from NASA to make the point. A telescope's light grasp is a measure of how much light is captured by the objective element. This depends on its cross-sectional area. Being circular, area depends on the square of the diameter of the objective lens or mirror. So, light grasp is proportional to area, which is proportional to the diameter of objective element squared. This means that if one telescope has an objective that has twice the diameter of another, its light grasp will be 4 times, that's 2 squared, greater. Another important feature of a telescope is its magnification. This depends on the ratio of focal lengths of the objective, f sub O, and eyepiece, f subscript E. So magnification is equal to the focal length of the objective, that is f subscript O, divided by focal length of eyepiece, that is f subscript E, where the two focal lengths have the same units, of course. The focal length of the objective element is obviously fixed, and so different magnifications are achieved by using eyepieces of different focal lengths. The shorter the focal length, the greater the magnification. A handy piece of kit, which we should be familiar with, is called a Barlow Lens, and that isn't actually an eyepiece, but allows eyepieces to be slotted onto it. The optical elements of a Barlow lens increase the magnification by a factor of 2 or 3, effectively doubling the number of eyepieces available to the astronomer. And here I've put an image up. The greater the magnification, the smaller the field of view of the telescope, so that's a consequence, of course. The field of view, sometimes abbreviated to capital F, capital O, capital F, a V, the field of view of a telescope is the circle of sky that is visible through its eyepiece. For example, in the central image here, the FOV is 5 moon widths, and the FOV in the right-hand image is slightly more than 1 moon width. So we're going to finish off telescopes, and then we're going to talk about space probes. So and as a bit of background, you might like to know that Italian astronomer and mathematician Galilei was the first scientist to use a telescope and interprets, I have to say often incorrectly, what he saw. Galileo's original telescope was a refractor with a convex lens on the objective and concave lenses for an eyepiece. The design was modified by the German mathematician Johannes Kepler, who replaced the concave eyepiece with a convex one, which is worth knowing. Right, so here we go. So let's just finish off a little bit about telescopes. I've put some of the names of the main pieces here. And there are many different types of telescope design, but most astronomers prefer to use reflectors, mainly because of the large objective apertures that can be manufactured and supported. It is difficult for large lenses to keep their shape. Also, unlike lenses that absorb light, it is possible for mirrors to reflect light with almost no loss in intensity. The Newtonian reflector is what we have here. You can see the plane mirror and the concave parabolic mirror at the end. The Newtonian reflector, where light is collected by a large parabolic mirror reflected up the tube and then sideways out of the telescope to focus by a small plane mirror. The image is then magnified with the eyepiece lens. Another problem with refractors is that lenses tend to focus different wavelengths of light to slightly different points, and that is known as chromatic aberration, making images blurred and unclear. Refractors also tend to be longer in size, although this can be avoided using prisms, as in pairs of binoculars, which makes viewing difficult and impractical at times. A diagram, again, showing the optical arrangement of the Newtonian reflector is shown here on the screen now. Another popular type of reflector is the Cassegrain reflector, which tends to be more compact than the Newtonian. So the Cassegrain or Cassegrain reflector, light is collected by a large parabolic mirror and reflected up and then back down the tube by a small convex mirror. Light then passes through a small hole in the primary mirror where the image is magnified with the eyepiece lens. Okay, so we're going to the last part about space probes. This is finishing off chapter 5. And you should be able to, in your exams, you should be able to give some advantages and disadvantages of manned space exploration. So what types of probes have there been? Well, exploring the solar system uses scientific instruments, of course, and unmanned space probes in one of the most exciting and challenging areas of space science. The four main types of probe are the ones that you need to know the names of. So we've got the flyby missions, in which the space probe explores many targets. Missions include Voyagers 1 and 2, that visited the outer planets, and New Horizons, that explored Pluto and the outer solar system. You have also a second class of space probe, which is the orbiters, such as the Magellan probe, that mapped the planet Venus using radar, Dawn, that made detailed studies of asteroids Ceres and Vesta, and Juno, that measured Jupiter's composition and magnetosphere. You also have a third type of space probe called the Impactors. We've already seen how the third stages of Saturn V rockets were impacted into the lunar surface to cause artificial moonquakes. More recently, the Deep Impact probe impacted on Comet Tempel 1 to study the internal composition of a comet. And lastly, we have soft landers, in which the impact is controlled and the probe touches down intact on the surface. Examples include Huygens landing on Saturn's moon, Titan, the Spirit, and Opportunity rovers to Mars and Philae, and of course we have the new Perseverance, don't we?